All right, AP Chemistry, this is the answers video for the reaction quotients assignment. So first, starting off with the definition, reaction quotient Q is computed the same way as K, the equilibrium constant. Where K is computed with equilibrium concentrations or pressures, Q is computed with the existing concentrations or pressures. And so we're going to see how it's used. So I start you off just with a review problem here. So we've got this, we've seen this before. Initial concentrations, and we assume 0 if nothing's given. Coefficient is 1 here, and 2 there, so this is going to be minus 1x, minus 1x, plus 2x. So this becomes minus x, x, and this becomes 2x. Alright, so I'll write the law of mass action up here, and everything here is a gas, although it doesn't state it there. We'll go ahead and write that, so K. However, even gases can be expressed as molarities. They don't have to be expressed as pressures. Okay, so K, concentration. Okay, so we're going to start off by writing the law of mass action here. Do it in terms of the chemical reaction. Don't just go straight to numbers. So it's the product there it is. Now you can plug in your algebraic equations. We'll do that down here. So for HI, it's the 2x. And I'm going to go ahead and just go to parentheses here. Okay, there we go. So now, if we assume that x is very small, and it is, because 2.6 times 10 to the negative fourth means very little is going to go over to the product side. Most of it is going to stay over here. So that means your change variable, this one right here, is not going to be very big. So if we assume it's small, we can eliminate the x's. Okay, again, if you add 5 to 1 million, you end up with 1,000,005. That's close enough to 1,000,000 that you could ignore the 5. Okay, so now we're going to square that, so it's 4x squared. Down here, this just is going to become 0.1, the x goes away, and 0.14, the x goes away. Again, that's called the simplifying assumption, and you'll always be able to use it on the AP exam. They will never give you one where you have to use a quadratic, okay? So now we're going to go ahead and plug in the value of Kc here, which is 2.6 times 10 to the negative fourth. Okay, so now you're going to multiply both sides by this and divide by this, and you'll end up with x squared equals this. Okay, so x squared equals 0.0091. Okay. And what we're trying to find is the equilibrium concentration of HI. First of all, we've got to find what x is. So we're going to take the square root of both sides. So that means x is going to equal the square root of 0.0091. And that gives us 0.095. All right, so remember, that's not your final answer. Your final answer is this. It's 2 times that because you're trying to find the concentration of HI. So the concentration of HI, which is what you're looking for, equals 1.9. 0.19. Let's do that right. 0.19 molar. And that's it. And that's a molar. It's a molarity. Okay, so you know the concentration of HI. If you took 0.14 minus 0.095, you'd get the concentration of I2. It didn't ask for that. and H2 would be 0.1 minus 0.95. You could get the concentration of H2. Now, if you have any concentrations other whatever those come out to be, the 0.19 and whatever these are, then you're going to, and you do the same calculation, you're going to end up with a number that's different than the equilibrium constant, and that's called the reaction quotient. And if the reaction quotient turns out to be less than the value of the equilibrium constant, that means the reaction, it means that the denominator is too big. So it means the reaction will move from left to right. So it's going to move in the forward direction if Q wants to approach Kc, it wants to move up to Kc. If the reaction quotient is bigger than Kc, it wants to move down to Kc. That's going to make the reaction move in the reverse direction. It's going to move from right to left. All right, so let's go ahead and practice a few of those. So you got an equilibrium constant of 8.7 and a reaction quotient of 6.5. So that means the reaction quotient wants to move up to be to 8.7. So it's going to move right. It's going to favor products. Okay. Here you have an equilibrium constant of 2.3. If you have a reaction quotient of 5.2, it's too big. It means you have too much product in the container, so it's going to move down. So it's going to move to the left. The reaction is going to move to go back and make more reactants and fewer products, and that's going to favor reactants. Okay, 69 times 10 to the minus 8, which would be 6.9 times 10 to the minus 7. But anyway, that's still a number smaller than this. So if this is smaller than this, it's going to move to the right. It's going to move up. So this is going to move up. So the reaction is going to move to the right and favor products. Okay, this is smaller than this. So again, it's going to move up, move to the right. Again, the reaction quotient wants to move towards the equilibrium constant. Okay, this one is bigger than this, so it's going to move down. This number is going to get smaller to be like that. So that's to the left. Okay, and finally this is smaller than this, so it wants to move up. So it's going to go to the right and favor products. Okay, that's all there is to that exercise. All right, so it says assume you have the same reaction equilibrium constants as in problem 1. Compute the reaction quotient for each of the following concentrations of H2, I2, HI. Then state which way the reaction will go. All right. So again, let's go ahead and write the law of mass action for that. So now though we're calculating Q. But the rest of it is exactly the same. All right. So you're going to plug these numbers in. So let's just do the first one together. We're going to do HI squared, so that's 0.0024 x squared equals, and I get some really tiny number. Now I'm going to divide by this and by this, by this and by this. So the 0.0024 goes there, the 0.2 goes there, I'm looking at this one right here, and the 0.5 goes there. So I'm going to divide by 0.2 and divide by 0.5. And that gives us 5.76 times 10 to the negative 1, 2, 3, 4, 5. Okay. And what was the equilibrium constant? It was 10 to the minus 4, 2.6 times 10 to the minus 4. So that means this is smaller than the equilibrium constant. It wants to move up. That means it's going to move in the direction of products, move to the right. Okay, I'll do one more of these. You can do the rest. All right. Okay, next up, now we have these concentrations right here. So we're going to square this one, 0.0004. We're going to divide that by 0.3 and divide that by 0.1. And that gives us 5.33 times 10 to the minus 1, 2, 3, 4, 5, 6. Okay, again, that's going to be smaller than our equilibrium constant of 10 to the minus 4. 2.6 times 10 to the minus 4, that means this is going to move up. So again, it's going to move to the right. If the Q is smaller than the equilibrium constant, it wants to increase the product, so it's going to move to the right. It's going to favor products. Okay. All right, let me just pick another one randomly. I'm going to pick this one down here. So it's 0.16x squared divided by 0.4 divided by 0.17. Okay, and that gives us 3.76 times 10 to the negative 1 power. Okay, that's going to be bigger than the equilibrium constant. Again, this number right here. That means this is going to want to move down. There's too much product. It's going to want to move to the left, and it's going to favor reactants. Okay, and that takes care of that. You can do the other three. Ask me if you want to check your answers, okay? All right, now we're moving down to some review. So the thing to remember, these are covalent compounds. They are the ones that use, you can number 1, 2, 3, 4. Okay, and this is mono, di. These are the prefixes. You use them in front of these, except you don't use mono, that should be mono in front of the first element. So carbon dioxide is CO2, well, it's what I just said, it's carbon, and it's 2 oxygen, so it's dioxide. You do not say monocarbon dioxide. Okay, these are pretty easy. Nitrogen, monoxide. Not monooxide, monoxide. Nitrogen. I know there's other names you'll look up on the internet. They'll give you different names for some of these, but I want you to use the naming that we're doing here. Monoxide. Bromine. Penta. Fluoride. Okay. Dinitrogen. Disulfur, dichloride. Okay, xenon tetrafluoride. Okay, so again, covalent bonds, let me get it on the screen here. Covalent bonds are the ones that use this, okay, not ionic bonds. All right, that takes care of this lesson.